In this case right here, what we want to do is rewrite this in the rectangular coordinate form. If you're looking at this right here, it's a bit awkward because we have this cosine of theta, but we want the r cosine. And we have this r squared here, but we just have an r. So the question becomes, well, how do I go about using these properties right here to convert between polar into rectangular? But the beautiful move that we're just going to do first here is we're going to multiply both sides of this equation by r. When we multiply both sides by r, you can see how probably beautiful this becomes right away. I get r squared over here, and I get 8r cosine of theta. Once I do that, I actually now have r squared. I can replace r squared with the xy right here. So I get x squared plus y squared on the left-hand side here. And then r cosine is the same thing as x, so this just becomes 8x. And then actually there we have converted this into rectangular coordinates. But the real power of doing this is to figure out what shape you have, or what is the figure you have in the rectangular coordinate plane to describe our original equation right here. So what I'm going to do is I'm going to subtract over this 8x and work with this just a little bit. So I have minus 8x. I'm going to put this y squared right here, leave a space, and then I get 0 over here. So just subtracting 8x from both sides. What I'm going to do now is an important trick when dealing with any kind of equations. I want to remind you of this. I'm going to complete the square with the x's here. When I do that, I take half of this linear coefficient value, this -8. I divide that by 2 to get -4 and square it to get 16. And so what I'm going to do is add 16 to both sides. So again, I'm completing the square. I know you've seen this. You probably haven't seen it recently, but we've done this. So when I complete the square, what I know is that this expression right here, I need a plus, sorry, in between those two. So I've added 16, I have as plus y squared. Here, this factors perfectly into x minus 4 squared. This is obviously stays as y squared, and then I have 16. And so in my mind, this is the best form of this rectangular equation, or this equation described in terms of rectangular coordinates. And by the way, real fast, just to describe this is a circle, we know, and it's centered at x equals 4, y equals 0, and it has with radius of the square root of this right here. And beautifully and importantly, we'll talk a bit about this in a second, but the idea is, what does the graph of this look like? Well, we've just proven that this right here describes a circle centered at the Cartesian coordinates of 4, 0 with a radius of 4. And important to say this is that even though we're describing it this way or this way, the shape, the physical shape that you see, the graph, will be exactly the same, even though we're describing it in 2 different coordinate systems. And then, as you may have guessed, what we're going to do is take a Cartesian coordinate equation and write it in polar form. Again, the first step of this won't be too difficult, but what we want to do, by the way, if I haven't mentioned it yet, is we want to get to a point where we write at r equals. So just like we like writing rectangular Cartesian coordinate equations as y as a function of x, so y equals a bunch of jazz with x in it, if we have a function. If we have a function in polar coordinate system, we want r equals. So let's show all that work here real fast. My first step is simply to replace x and y with the representative polar coordinate expressions here. So this becomes r cosine of theta plus 2 squared plus r sine of theta plus 3 squared equals 13. Then what I'm going to do is expand these out. This is going to look a little nasty, but you'll see how it cleans up nice. But when I expand this out, what I get is r squared cosine squared of theta plus 4r cosine of theta plus 4. So that's me expanding this expression right here. Exactly the same treatment with this will give me r squared sine squared of theta plus 6r sine of theta plus 9 equals 13. So things just got kind of intense looking. It's going to clean up really nice, and usually will for the kind of problems that you'll be dealing with. But first things first, I'll remind myself what I'm trying to get is R equal an expression in terms of theta. But let's clean this up before we get there. The constants work out really nicely here. So this is a 4, this is a 9, and this is a 13. Those all cancel when I subtract 13 from both sides. Then what I'm going to do, and I won't write out these steps, but I'm sure that you can see this real fast. What I have is r squared cosine squared plus r squared sine squared. So if I bring this r squared sine squared with the cosine squared, and then I factor out on r squared, what I'll have is r squared times sine squared plus cosine squared. But I know the cosine squared and plus sine squared is 1. So I just get r squared times 1. In other words, these add together to just give me r squared. And then I still have these two terms right here. So plus 4r cosine theta plus 6r sine of theta. And now equaling 0. Then this next step is actually just the opposite of what I did to start the last problem. If you remember, I had this r equals 8 cosine theta, and I said, well, I want to get some r squareds in there and get the r cosine to input this information right here. I'm going to do the opposite now. What I'm going to do is divide both sides of this equation by r. And when I do that, I'll end up with r plus 4 cosine of theta plus 6 sine of theta equaling 0. And then just to rewrite this in terms of r in terms of theta. So what I'll do right here is just subtract over these two terms to get r equals negative 4 cosine of theta minus 6 sine of theta. And again, to remind you of what this is, as we talked about in the beginning, because these will describe exactly the same graphical shape, and because it's going to help the conversation we're about to have with graphing or looking at the graphs of these polar equations. This is a circle. So this describes a circle. It's centered at negative 2, negative 3, and it has a radius of the square root of 13.